Hello, my name is Nilay Juglekar, and I'm presenting our work on suture thread spline reconstruction from endoscopic images for robotic surgery with reliability-driven keypoint detection. As a form of brief introduction, suture thread reconstruction is an important subtask for automating suturing. It's important to know the 3D configuration of suture thread in order to choose grasping points and to plan tool movements. However, there are a couple considerations when creating such a method. For example, suture thread is incredibly thin and noisy in surgical images, so it's important to have some form of a reliability metric in order to avoid placing false confidence in your results. In addition, it's important to have a smooth and well-parameterized reconstruction in order to ensure that it's more realistic and to help with visual servoing down the line. Our specific contribution is a suture thread reconstruction and spline fitting method, utilizing reliability-based keypoints and a minimum variation spline optimization. This pipeline is shown on the right. Moving on to our method, the first step involves stereo matching on lifted images. After we perform stereo rectification and segmentation, we can lift the thread features from each image by subtracting the background, leaving the thread features intact. Once we have these lifted images, we can perform stereo matching and create a depth map, as is visualized on the right. However, as you can see, this depth map is incredibly noisy. This brings us to the next step in our method, which involves finding reliability-based keypoints. We use a disparity reliability metric, as shown on the middle left, to create a reliable pixel set. This metric works by comparing the best disparity with the second best disparity, and if these assigned to each pixel. And if these disparities are too similar, then the disparity is less reliable. Once we have this reliable pixel set, we can cluster it using breadth-first search, as shown in the video on the bottom left. Once we have these clusters, we take their centroids and call those keypoints. These keypoints are visualized in the video on the right. And as you can see, they are much less noisy than the original depth map. We can go further and order these keypoints using a series of BFS and DFS operations. Once we have the ordered keypoints, we can move on to computing a minimum variation spline from keypoint-derived constraints. We define boundary points above and below each keypoint based off of local variation in the keypoint set. This local variation is measured by taking a set of local keypoints around a single keypoint, and then fitting a line to this set. Once you have this line, you compare your current keypoint to that line and see how far away it is from it. If it's further away, then the boundary around that keypoint should be larger. This boundary is visualized using the yellow lines on the video on the right. Now we can move on to our MVS optimization. This optimization has two types of constraints, as are shown on the bottom. The first constraint are the boundary constraints, which we talked about earlier, which ensures that the computed spline stays between these keypoint defined boundaries. The second set of constraints are for the endpoints, limiting them to a certain position and slope. The objective function for this optimization focuses on reducing the change in curvature along the length of the spline. Finally, we can visualize this process in the image on the right, in the video on the right. Now we can move on to our results and our conclusion. We tested our method on both a simulated dataset and a real dataset. In the simulated dataset, we compared our result with the ground truth curve using 3 metrics: a mean reconstruction error, a max curve error, and a length error. In addition, we tested our method on a real dataset, and we evaluated this using a reprojection error, as well as a qualitative metric. For the qualitative metric, we rated bad reconstructions with a 1 up to very good reconstructions with a 5. We also show some failure cases of our reconstruction, as is shown on the bottom. Also, for further context, the ground truth line is green, while our reconstruction result is red. This brings us to our conclusion. To highlight a couple a couple findings from our results. Our reconstruction was on average just about 1 millimeter, which is very accurate. In addition, we had a reconstruction success rate of about 80% on both the simulated dataset and the real dataset. Moving on to highlights for our specific method, our method requires no user input. The reliability metric, although it's useful for reconstruction, it can also be useful for grasping in the future by evaluating which points on the thread are most reliable and most accurate. Lastly, because we use a smoothing method, our results are more realistic. Thank you for watching.